Today we're going to code the Big Bang using Python. We'll start by creating an array of objects which will represent our galaxies 1 billion light years apart. So there they are. And then we're in a loop, we're going to move those galaxies. So they'll be moving by hd. And d is its distance, and h is Hubble's parameter. So there they go. All the galaxies are moving apart. We can show their distance at each step down below. Next thing we're going to do is add a photon. So the speed of light will be 1 million light years per million years, and its distance will start at 0, and it will move by the speed of light. So the photon is going to pass some galaxies, but then the galaxies are going to start passing the photon. We don't want that. We want the galaxies and the photons to be moving at a similar speed. So the photon is going to move at c plus hd, which is the speed of the galaxy it meets plus the speed of light. Now we get this, and that is much better. And we can calculate a redshift by taking the ratio of the new speed over the old speed, and that's like taking the ratio of the new wavelength over the old wavelength, and since that's equal to 1 plus z, then we can say minus 1, and that equals z. If we store that z, the redshift, and we store the distance that the object was when it met the photon, then we can plot them like this, and we'll see that we have a constant expansion rate. Now let's review. Variables can have any letter, including Greek letters. These are lambda and omega. The standard model of cosmology is called Lambda CDM, and its expansion rate is not constant. Its parameters are h, Hubble's parameter, which we've already seen, and we have h subscript 0. This is Hubble's constant, and that's the current expansion rate. Omega lambda is how much of the universe is dark energy, and omega m is how much of the universe is matter. When the universe expands, its volume goes up to the power of 3, one for each dimension, but the density of the matter in it goes down by the power of 3. With dark energy density, expansion doesn't change that at all. So we get this expression omega m times 1 plus z to the third power plus omega lambda. We can use that to calculate an expansion rate. Now, when the expansion rate is constant, then h always equals h0. That means that this expression for all z's has to equal 1, which is true when omega m equals 0 and omega lambda equals 1. This universe is known as a pure dark energy universe, an exponentially expanding universe, and a de Sitter universe. It's a very useful model, but it is wrong. So we need to change the expansion rate at the bottom of our loop here by adding that equation. We also need to define now Hubble's constant and our omega values. See, omega lambda equals 0.7. That's for 70% of the universe being dark energy. Now, if we run this, we'll see that things get out of control pretty quick. As the redshift goes up, so does the expansion rate, which means that redshifts faster, which means it expands faster. So we get this. This is supposed to be the history of the universe's expansion, though, and we're calculating the future of the expansion. So we can trick it by setting Hubble's constant to a negative number. Now, instead of an expanding universe, we'll get a contracting universe. It's expanding, but this is going backwards in time. Now the photon isn't reaching the origin, it's leaving the origin, but it's actually being received at the origin backwards, if that makes sense. To calculate redshift properly in this universe, we'll need 2 photons, initially separated by 0.1. So P2 has a little bit of a head start, and now the redshift is 0.1 divided by their distance in the past. It should get smaller, the universe should, so the distance should contract. So that is our new redshift calculation, and with that, we get something like this. Well, what's that? That's the Big Bang. We did it. That's what we were going for. Everything goes back to a singularity. This turnaround point is pretty interesting. You should check out episode 4 if you want to learn more about that. Now, when the universe expands, light will be emitted from one distance, but when it's received, the galaxies will be at another distance. Now, that distance, the ratio of those distances, is equal to the ratio of the old and new wavelength, which is 1 plus z. A third distance is the light travel time distance, shown in yellow there. So if we single out a galaxy in our model, we can point where the distance at t emit is, and that's right there, and the distance now is up at t equals 0. The distance the light traveled at is given by this. So let's compare our model to something more official, like cosmology. So we'll take a range of z's, and for each z we'll calculate the distance at t now using the co-moving distance function, the distance at t emit using the angular diameter distance, and the travel time using the look-back time function. And here we have the data. So we go back to our model. How does it compare? Well, we don't actually need these blue lines to calculate any of that, so we can get rid of that, which simplifies our code quite a bit. So on each step, we'll add to an array, we'll add the redshift z and the distance at t emit, which is the photon distance. We also know that the distance now should equal the photon distance times 1 plus z. And we also haven't been keeping track of time here, so we'll do that now, and we'll say that time's going backwards by 1 million years at a step, and then we can save that in the array as well. Now this Hubble's constant, we want something standard so we can compare it accurately. So we're going to set that to 70 in kilometers per second per megaparsec, which is the standard units, and the next line just converts it there to million light years per million years per million light years. And since that's no longer a negative number, we just need to change the c plus hd of the photon speed to c minus hd. Now, when we compare all that, we get identical results to cosmology, which I think is pretty interesting. That's a nice, small, tidy function, basically, that does all the work as that complicated calculus. So one more thing, that while true, we obviously don't want to use that because then we'll be stuck in a loop. You should do something like while z is less than 10. Say you want to find the distances for a redshift of 10. You can use this. Or if you want to find the redshift given a distance, you could do that too. Or you could find distances in redshift for a time. Even the recession velocity. This will show the cosmic turnaround. So it's a really versatile function that way. Check out the Jupyter notebooks. They're on GitHub. The links are in the description. Thanks so much for watching. I hope you learned a bunch and had some fun.